Hi, I'm Xander Neuwirth, and today I'll be talking about architecting and visualizing deep reinforcement learning models. This is a summary of some work that Dr. Derek Riley and I put together last quarter at the Milwaukee School of Engineering. Just to start off, I'll give a brief overview of deep reinforcement learning. So, in DRL, your agent, that's the AI that you're building, performs some actions in an environment. And you assign reward to these actions based on some sort of overall objective. Uh, and if an action takes you closer to that objective, you give it a positive reward. If it brings you further away from that objective, you give it a negative reward. And the goal is to develop an agent that is capable of intelligently looking at a state and determining which actions can maximize that reward. In DRL, you use a neural network to approximate that policy. So you're building a neural net that looks at the state of your environment and comes up with its best guess at what actions will work. And this technique got really popular around 2015 when Google DeepMind put out a really cool paper on deep Q learning, which is a type of DRL, and used it to develop an AI that was capable of, with no prior experience, teaching itself how to play at a superhuman level various Atari games. And this has inspired a lot of really cool work. Go is a board game famous for being really difficult for computers to effectively play, and recently AlphaGo used DRL to defeat the world champion. There's been other really cool work, for example, in robotics, interacting with messy real-world systems. DRL has been used pretty successfully in that domain. And even for stock prediction, DRL has shown a lot of promise in automatic trading bots. And that's just the tip of the iceberg. There's new and interesting work coming out every day, and there's plenty of other really cool applications of this stuff. So inspired by that, Dr. Riley and I set out to build an educational tool, something interactive that is easy to understand, really visual, interesting to watch, and even fun. And we were hoping to demonstrate a lot of these key DRL concepts to someone who might not have familiarity with even computer science in general. So we were hoping that they'd be able to take a look at our visualization and get some meaning out of input shape, how the network is able to perceive its environment, how it's able to output its actions into the environment, and even the inference process of taking that input and synthesizing some sort of intelligent idea of what a good action might look like. So to achieve this, we started out by creating a Pong environment. This is just a game engine that is capable of running the Pong game. It takes in paddle input up, down for both left and right, and runs all of the calculations for where the ball is, how it bounces, what constitutes a score, collisions, all that. And of course, the interesting bits are these agents. Now, this left agent is just a hard-coded opponent. It has full knowledge of the game state, what X and Y coordinates everything is at, and it exists only as something to train our agent against. So it follows a strategy like, if the ball is above me, go up, if the ball is below me, go down. Something really simplistic like that. And this right paddle is the agent we're creating. It takes the pixels of the game state and intelligently tries to come up with an action that's best for that state. And then finally, we have our visualization piece. And this takes in the game pixels and also all of the details of our agent, the model structure, the weights, the activations, all that good stuff, and puts that up on the screen so that the user can tell what's going on and hopefully get an idea of the inference process and how this all works. So our neural network is pretty straightforward, all things considered. The input is just the game state diff. So it's not exclusively one state. We take each state and subtract it from the state that came before it. And what you end up with is a bunch of ones, negative ones, and zeros. The ones indicate where there's paddle or ball but wasn't before. The negative ones indicate where there uh, was paddle or ball in the previous frame, but now it has moved away from there. And any place that has been constant, just as background or as being occupied by paddle or a ball, that's just empty. That's zero. And the network architecture is pretty straightforward. We have a single dense layer, 200 neurons. Every neuron is connected to every single pixel in the state. And our output, simply two dense neurons connected to everything in the hidden layer. And it uses categorical cross-entropy to generate a probability distribution of how confident it is in each action across the action space. So in this diagram, I have up and down. For some of our tests, we also used a stay stationary, do nothing action. But we ended up scrapping that for the final design for reasons that I'll get to later in the presentation. And the way we train this network is also pretty straightforward. So we randomly initialize it to begin with. So all the weights and biases of the neural net, just complete random values. And we feed in each game state. It predicts an action, and initially these are basically random values, so it performs pretty terribly. But we take the action that it thinks is better, so in this case it would be down, and apply that to the environment. So we tell the right paddle to move down, and the environment returns the next state for us and the reward. And the reward will be 1 if our agent scores, -1 if our agent is scored upon, and 0 if there isn't a score for that frame. And the next state allows us to repeat this process indefinitely until one side scores 21 points and the game is over. So we've saved all of the game states, the predicted actions, and the rewards throughout this whole process. And after we've completed a batch of games, we can try to improve the network's behavior. And we do this, first of all, by doing something useful with our rewards. Right now, these aren't too valuable because they only give us a sense of whether the action is good or not on the frame where there was a score. And in reality, that's not really what we care about. The frames where there is a score is only a very small part of the game. It's all of the frames leading up to that, and it might be 10, 20 frames before the score where the paddle actually missed the ball or successfully hit it at the opponent. So we need to assign blame to these scores to the frames leading up to them. And we do this by discounting it back, effectively. We kind of exponentially decay these scores back through the frames before them up until the previous score. So we end up with something more like this, where we have the score, and then the frame before that it's like 0.99, 0.98, all the way back to 0.4, and then we have the previous frame where it was scored upon. And you can see all of the blames have really been smeared back, so we have a decent sense of whether each move was good or bad eventually, and how confident we can be that this move actually contributed to that score. Because the further back we get, the less we can really be sure that this was a good move or not, or contributed to the eventual score. Now that we have more useful rewards, we can calculate this idea of a gradient. You can think of this as how much we want to nudge what we actually predicted to form a more reasonable prediction, knowing how it actually played out. And this is calculated as the action we selected minus the probability we output. And this is all multiplied together by the reward. So what this effectively does is it gives us a negative value if we decided not to do something, and a positive value if we decided to do something, scaled by the confidence. And then all of this is scaled again by how it eventually played out for us. And notice that this reward flips the sign. So if we confidently said that we shouldn't do something and then it backfires and we're scored against, that negative reward will flip the sign and the gradient will tell us to do the opposite thing. So this actually ends up being a really intuitive calculation. And we can use it pretty directly to come up with our label for the data. Or rather our label for each frame, what we think that the predicted probability should have been. And this is meant to be just a pretty small nudge at our previous output to make it more reasonable. So we calculate this as our probability, the previous output, plus the gradient that we came up with times some small learning rate. So in our case, we use 0.001. So it takes this gradient, makes it very small, just a tiny nudge to our previous output, and declare this to be what the output really should have been based on how it played out. And you'll see these are pretty small tweaks. Um, these are sort of meant to reflect a reasonable label given this probability. And the difference is pretty hard to detect, but if we do this over and over and over again, um, it has a cumulative effect and the policy improves gradually over time. And we do actually execute this a ton of times. We have these game states and these labels, and we do these games in batches of 10 games played to 21. We run all those calculations to get the states and labels, and we run one epoch of backpropagation across the neural net. And after doing that, we repeat the process, generate another batch of games with the new policy, and repeat this until we've played somewhere in the realm of 80,000 games. And at that point, the policy stops improving, the scores remain relatively constant, and we can stop training and deploy the model. So we actually ran into quite a few challenges with this approach, which was surprising at first because the environment is really simple, but it's actually these simplifications that cause some interesting issues. So the pixel subtraction information loss was a big one. Since you're subtracting each frame from the previous frame, you're inherently losing information, and some of that information is actually pretty important. Um, Particularly the case where the paddle doesn't move is really problematic because when our agent didn't move the paddle, uh, it was subtracted from itself in that frame diff and doesn't appear on the screen, which means the agent doesn't know where it is and it can't react intelligently to the ball coming at it. And we ended up fixing this with a bit of a hack, just disabling the ability to not move for our agent. So it's constantly wiggling and constantly appears as a diff on the screen. Um, Ideally, in a future model, we'll work around this and maybe don't calculate the diff across the paddle or something to that effect. Um, but for now, this worked perfectly well in letting our model train a little bit better. There's also some information loss from the downsampling. So we downsampled by a factor of 4 between the pixel output and that actual model input. But this had some interesting effects where if the ball was small and moving at a weird angle, uh, it could actually blip in and out of existence just because of the way that the downsample was estimated. So we ended up making the ball bigger and running a couple other tweaks in response to that. One of the more interesting challenges we ran into was overfitting on the opponent's AI. So this is the hard-coded opponent that our agent trains against. And at first, our strategy was that this hard-coded agent would basically follow the ball all the time. Uh, and wherever the ball was, this paddle would try to be in front of it. Well, the unforeseen consequence of that was it trained against this opponent really well. But as soon as you swapped it out for a different opponent, like a human player, it worked really poorly. And this ended up being because we were overfitting against that paddle. We were using it as an extra indicator of the Y position of the ball, to the point where we were barely looking at the ball at all to determine what its Y position was. And we ended up having to fix this by adjusting the behavior of the AI so it was less predictable and not a good indicator of that ball position. And then one other side challenge, it was surprisingly difficult to judge how well that our agent generalized, how well it performed against a human, without actually playing against it, which is a little bit of a time-consuming process. And if we're training a lot of models, it's not really wieldy to do that. So that was just an annoyance that We sort of overcame by having it play against a couple different hard-coded AI, so we could better assess how it generalizes, but it was just something interesting to note. So we, of course, optimized this agent as well once we had a working model. One of the things we played with was network structure. We experimented with a few network structures. And while the visualization uses this model of 200 neurons, if we deploy it, we hope to update it to use the more in-depth, higher performing models. We kept it small, small dense structures, just so it would still be easy to visualize. But you can see, compared to that baseline, we were able to come up with structures that perform quite a bit better. Another experiment we ran was ball diameter. And this is actually a test of a 6-pixel diameter ball. All of these tests were run on a 2-pixel diameter ball, and you can see the difference is pretty remarkable in how quickly and how well this thing scored just by making the ball a little bit bigger. And it's actually barely noticeable. It's still a very reasonably sized ball. So for the final deployed environment, we'll probably include this change as well, just because it boosts the AI's performance quite well. And once we had a working model, we were able to develop our visualization. And there's a lot of stuff going on here, but I'll try to break it down. So all of these nodes represent the neurons in the hidden layer. And the size roughly corresponds to how large the bias is for each node. And the red nodes are, of course, activated at a given time. And these red lines between nodes indicate activations as well. And the effect is this runs in real time. All right, that's what we were able to build. If you have any questions at all, definitely check out the paper. It's linked in the description and has a lot more detail on some of these things. It also has citations for a bunch of the things I referenced in the presentation. Feel free to leave questions or comments in the video comments, especially for the duration of the conference. I'll be checking those periodically, and feel free to contact me at my email right there. I hope you got something out of this. Thanks for watching.